Hey, my friend Arthur Moore is here. Hope all is well. In this video, we're going to look at inverse trigonometric functions and integration. Theorem 5.17 here says the integrals involving trigonometric functions can be found by, if we let u be a differentiable function of x and a is greater than 0, then the integral of du over the square root of a squared minus u squared, where a is a real number and u is some variable, equals arc sine of u over a plus c. The second one, the integral of du over a square plus u square equals 1 over a arc tan of u over a plus c. And the integral of du over u times the square root of u squared minus a squared equals 1 over a times arc secant of the absolute value of u over a plus c. So the first thing that we have to do is find the form that matches one of these three, and then use substitution. Let's identify the u and the a and then use substitution if possible. All right, so we don't have to use a substitution method. We just need to be able to identify u and a and du, of course. So in number one here, we have the integral of dx over the square root of 9 minus x squared. So we know that 9 is a perfect square. We can rewrite that as the integral of dx over, and if we break this down, 3 squared minus x squared. So now we can identify 3 as being in the place of a, and x is u, I think. So let's let x equal u, or u equal x, and let's see, du would equal dx, which is what we needed. All right, so let's go and see what that matches up with. That seems to match up with number one from our theorem, du over a squared minus u squared. So that is equal to arc sine, or the inverse sine, of u over a. So u is equal to x. We said a is 3 plus c. Alrighty. Number 3, we have the integral of 1 over x times the square root of 4x squared minus 1. And if I had to guess, I would say it looks similar to number 3, but we need to go ahead and identify our u and a and du to make sure everything matches up. Okay, so dealing with these perfect squares and the radicals, that's one way to help you see those trigonometric functions in the perfect square. So we have 2x squared minus 1 squared. So we'll let u equal 2x, and that means du equals 2 dx. All right, so normally we would divide both sides by that 2 to match up with that 1 dx. But remember, if we go back and look at 3 here, I have u on the outside and u squared on the inside. If I come back down to my problem, I have x on the outside but 2x on the inside. So I actually end up needing this 2 this time to make this x on the outside into 2x. So u would be the same. Those two values for u would be the same. So let's write this. So if we wrote this in terms of u, that would look like and we do need, let's go ahead and divide this or multiply by 1/2. So that will equal that 1 dx. So that will give me 1/2 times du. Okay, so now if I bring this 2 and multiply it here, I would have 1 over, and write this back in terms of x, I would have 1 over 2x times the square root of 2x squared minus 1 squared dx. And now I see that this form matches theorem part number 3 of the theorem, du over u squared over u times u squared minus a squared. So the 2x is in the place of u and the 1 is in the place of a. So that is equal to 1 over a times arcsecant times of the absolute value of u over a plus c. So 1 over a, 1 over 1, times the inverse secant of u over a, so the absolute value of 2x over 1 plus c. And then of course you can clean that up. So the inverse secant or arcsecant times the absolute value of 2x, or the absolute value of 2x plus c. Alrighty. Number 4, we have the integral of 12 over 1 plus 9x squared. So again, let's go ahead and let's let u equal 9x. Let's go ahead and integrate first, or break this down and make this 1 squared plus 3x squared. So let's let u equal 3x. Therefore du equals 3 dx, which is not that 12. So I'm going to bring the 12 to the outside. I'm going to go ahead and divide. So bring the 12 to the outside here. And then up here where I let du equal 3 dx, I'm going to make that 1/3 of du equals dx. So that 1/3 will also come to the outside and be multiplied times the 12, because it's replacing the 1 dx, and that's the constant multiplier. All right, so it looks like we have the integral of a squared 1 over a squared plus u squared. So let's go back up to our theorem here. And that looks like number 2, the integral of du over a squared plus u squared, which equals 1 over a, the inverse tan of u over a plus plus c. So 1 over a, so we have this 4 here, of course. And in this case, a is 1, u is 3x. And then u over a plus c. So we have 4 times arctan, or the inverse of tangent, of 3x plus c. Alrighty, number 5, we have the integral of 1 over the square root of 1 minus x plus 1 squared. So this looks similar to, this is in the form of a, the square, 1 over the square root of a minus u squared. Okay, so a squared minus u squared. Let's look and see what that looks like. Number 1 here, where we have the inverse, where we have this equals the inverse sign of u over a plus c. All right. So if u is equal to x plus 1, and then du is equal to 1 dx, that matches up. And we see that this is a, that's u. So in that formula it said that the integral of du over the square root of a squared minus u squared is equal to the inverse sign of u over a plus c. righty, that was fairly simple. Okay, what about number 8 here? We have 1 over the integral of x times the square root of x to the fourth minus 4, and that looks like that secant. Remember the secant. So if we have 1 over u times the square root of u squared minus a squared du, that equals 1 over a times the inverse secant of the absolute value of u over a plus c. All right, so let's go ahead and rewrite this as x squared squared minus 2 squared dx. And looks like for du, let's let u equal x squared and du equals 2x dx. Okay, so we need, again, we need these two to match up. Okay, so to solve for this 1 dx, we have 1 over 2x du equals 1 dx. If I divide both sides by 2x, okay. All right, so we can bring the 1/2 to the outside because we don't need that 1/2, but we do need this x to multiply by this x that's outside the radical. So we would have x squared on the outside and x squared on the inside. So let's make that 1/2 over 1, and then multiplying x times x gives us x squared, and then x squared squared minus 2 squared, and write that back in terms of x with dx there. All right, so that is clearly in the form of what we have above, 1 over u times the square root of u squared minus a squared du, which equals, so let's remember we have the 1/2 there, and then 1 over a. In this case, a is equal to 2 times the inverse secant or arc secant of the absolute value of u over a plus c. All right, so since we know that x squared, that variable squared, is always positive, then we don't have to keep that absolute value symbol there. We can let that go because x squared will always be positive. Okay. All right, let's look at another one. All right, completing the square. It says completing the square helps when quadratic functions are involved in the integrand. For example, the quadratic x squared plus bx plus c can be written as the difference of two squares by adding and subtracting b over 2 plus 2 squared. So hopefully you remember the process of completing the square. So the reason we want to do that is if we can make these into perfect squares, then we could probably use one of those 3 theorems that we just looked at. So number 35 here, we have the integral of 1 over x squared plus 6x plus 13 dx. So if we can take that x squared plus 6x and make it into a perfect square trinomial, then quite possibly we'll be able to use one of those theorems, one of those parts of the theorem we just looked at. So to make this into a perfect square, we have to half the middle term and then square it. So half of 6 is 3, and 3 squared is 9. But to make sure that this stays equivalent to the original. If I add 9 in this expression, I need to subtract 9 in that same expression, because 9 minus 9 will be 0, and the expression will still be equivalent to the original. But what this allows me to do is to factor that x squared plus 6x plus 9 to x plus 3 squared, and then 13 minus 9 is positive 4. So I can rewrite this as 1 over x plus 3 squared plus 4 dx. And that allows us to say that u is equal to x plus 3, du is equal to dx, 1 dx, which is what we needed there, so we're good there. And we know that the a squared plus u squared, or u squared plus a squared in our denominator, that's equal to that inverse tangent or arctangent form. So the integral of du over a squared plus u squared is equal to 1 over a times the inverse of tangent u times of u over a plus c. So in this case, we know that u is x plus 3 and a is 2, so 1 over 2 times the inverse of tangent of x plus 3 over 2 plus c. So I know that takes us back a little bit to completing the square, but hopefully that jogged your memory pretty good. All right, let's look at one more problem. All right, number 37 here, we have the integral of 1 over the square root of negative x squared minus 4x. So again, here we don't have a perfect squares down there, so let's try completing. We have a quadratic in our denominator, so let's try completing the square again. Before we complete the square, I like to have that first term to be positive, so I'm going to factor out a negative 1 to make that x squared plus 4x. Negative times x squared plus 4x. And then I'm going to complete the square. So x squared plus 4x, that means that I'm adding 2 and I have to subtract 2. And not 2, let's try it again. Half of 4 is 2, 2 squared is 4. Should be adding 4, so I have to halve the middle and square it, and then subtract 4. Okay, keeping in mind that I had that negative outside of that whole thing. Yeah, right here. So let's go ahead on the left hand side and clean this up. So we have x plus 2 squared minus 2 squared, which then if we distribute that negative back in, that will make negative x plus 2 squared plus 2 squared. Now, I know I didn't have any with the negative at the front, so let's flip this around and let's make this 2 squared minus x plus 2 squared. All right, so now I can come back over to my problem here and write this as 1 over the square root of 2 squared minus x plus 2 squared. So that's a squared minus u squared, and let's check the u. U is equal to x plus 2, and du is equal to 1 dx, so we're good there. So that equals the inverse sign, where we have du over a squared minus u squared. That equals the inverse sign of u over a plus c. So the inverse sine of x plus 2 over c. And that's it for this lesson, my friend. I hope you found it to be helpful, and I will see you on the next one. Thank you.